Almost there, guys. So in this video, what we're going to talk about is we're going to talk about not necessarily substitution, but elimination and how we can use that for synthesis. One of the first things I want to think about is that we've talked about already how easy it is to make an alkene using an elimination, specifically E2, because it doesn't give us that pesky SN1 substitution product. But what we haven't mentioned is, okay, one pi bond is good, but can we make two pi bonds using elimination? So specifically, can we make alkynes? Absolutely. And so what I'd like us to think about is that alkynes are made via elimination in a very similar pathway in the way that alkenes are. So for example, if we've got this vinyl halide, so in this case a vinyl chloride, what we can do is we can take a base and we can deprotonate this vinyl hydrogen and essentially do an E2 type elimination to give us our alkyne plus our protonated base. And in this, we'll say our base was initially negative. And so it turns out that for this type of reaction, not any old base will do. We tend to think about strong bases as things with hydroxides. So for example, sodium hydroxide is what we use to clean our drains. Here, it's actually not strong enough to perform this type of elimination. We need a base that is actually even stronger than what we could normally consider really strong bases. And so the type of things you're going to want to use for this are type of bases are the strongest of the strong. What you use to deprotonate something that's really not terribly happy about being deprotonated. So specifically, one thing that's very common is LDA, so lithium diisopropylamide. We talked about this earlier as a bulky base, so something that's not nucleophilic, but it's also very good at performing deprotonations that aren't necessarily happy about being performed. Again, the classic one for this is sodamide, so NaNH2. Metal hydrides will often do this as well, depending on which one you pick. So we'll talk sodium hydride here. And then finally, sort of, if you've got something that needs deprotonated and nothing else will work, you can use an alkyl lithium. The reason people tend not to use these, so this is N-butyl lithium here, is that they're generally not terribly selective. In the fact that it's such a good base, if anything else is slightly acidic, you'll probably deprotonate there as well. And so just a reminder, LDA, this is sodamide, generally, also something like LDA is just easier to work with than something like N-butyl, which often tends to be pyrophoric. Okay, and so, for example, when you've got something like this vinyl bromide here, and we treat this with a strong base, we wind up making our alkyne. Let's talk mechanism. I realize we've done this up here, but we'll show this again. And in this case, we'll use something like NaNH2. Pull off the proton. Keep in mind, there are two protons here. We do our E2 type elimination. Giving us our alkyne plus our protonated sodamide, which winds up being ammonia. So we got a little bit of sodium bromide plus ammonia. Okay, so that being said, something really kind of interesting happens when you have a terminal alkyne. So an alkyne, which is on the end of a carbon-carbon chain. And what that interesting thing winds up being is that our terminal alkyne is actually fairly acidic. And remember, earlier in this chapter, we talked about alkylation of terminal alkynes. And the first step in that was, okay, we pull off the proton. It turns out the exact same base we used to pull off that proton is the base we use to perform this elimination. So generally speaking, when you're making terminal alkynes, this reaction will simply go too far. And it will go ahead and deprotonate as well. Giving you the alkynolate as your final product. So if you do want the terminal alkyne, just remember you've got to throw something in there that is willing to give up a proton And this does not have to be a good acid. Remember that the lone pair of electrons on this terminal alkyne is a true carbanion. It is not happy to go ahead and bear those extra negative charges. And so, by throwing in something even as weakly acidic as water, we'll go ahead and protonate that and give ourselves our terminal alkyne. Okay, so let me just shift the camera. So it turns out that oftentimes we don't necessarily feel the need to start with a vinyl halide, like vinyl chloride or vinyl bromide. You simply start with an alkane with 2 halogens on it. And so an example of this would be the elimination from this dibromide here. And so we'll title our notes here, alkynes are often made with 2 successive deprotonations from a geminal or vicinal dihalide. Okay. And so what I mean by geminal or vicinal is just on which carbon these halogens are present on. So a geminal dihalide comes from Gemini, meaning twins, and that means that both of our halogens are on the same carbon. They're quote-unquote twinsies. On the other hand, if the bromine is on carbon 1 and carbon 2, and they're right next to each other, they can do these 2 eliminations. These are what are referred to as a vicinal dihalide, in that they're close but not quite. And so what will happen typically is when you've got this geminal or vicinal dihalide, we are going to add an excess of strong base. And typically this is done by just showing XS here. And you do this in a polar aprotic solvent. Polar aprotic solvent. You'll do your 2 eliminations, but remember, if your dihalide produces an alkyne that is terminal, you'll pull off that proton in the end. And so in this case, we'll actually do that. So 1, 2, 3, 4, 5. We'll have our alkynolid, or the carbanion of an alkyne here. And so if we would want the neutral alkyne, we'd wind up adding just a smidge of acid. So it can even be something like HCl, or water, or an alcohol. We'll protonate that sucker on, giving us our terminal alkyne. That being said, we've also done some chemistry here where we can actually substitute this terminal alkyne using an SN2 reaction. Realize that oftentimes what you'll do is in one fell swoop, you'll deprotonate, and in the same pot, then just add in something like methyl iodide to cap off this end with the methyl group. Okay, so we've got one more video after this where we're going to talk about forming non-Zaitsev products, and after that, you guys are free to enjoy your snow day. Okay.